Hello everyone and welcome to another PAT Problems video. My name is Helena and I'm the Access and Outreach Manager for the Department of Materials at the University of Oxford, and today we're going to be going through another PAT problem. So today we're going to be taking a look at one of the maths questions from the 2012 PAT paper. So we're going to have a look at question 10, which is all about sketching a graph of a function given some facts about that function. So we have to deduce what the graph looks like based on these properties. Okay, so let's have a look. Sketch an example of a real function f of x, defined for all real arguments of x, which has all of the following properties. Okay, so let's take a look at these one at a time. So the first one, f of x is greater than 0 for all x. Okay, so we're not going to have any negative f of x values. So when we're sketching, we only need to consider the positive values for f of x. Okay. Second one, f of x is a continuous function. Okay, so what does this mean? This means that we've got a smooth curve going on, that we haven't got any steps or sort of kinks in the graph. It's all a smooth curve. Okay, so that's something good to know. The third one, df by dx is 0 only for x equals 4. Okay, so the first derivative of the function is 0 only at this value. So what does it mean if the derivative is 0? Well, it usually means we have a turning point of some description. So we're told the x value for which this occurs, but we're not told anything that might help us determine the nature of this turning point. So for that, we'd want to know the second derivative of the function at this point. So from this statement here, C, we can deduce that we have some form of turning point at x is 4. So whether that's a maximum or a minimum at x equals 4. And finally, we're told that the second derivative of the function is 0 only for x equals 2 and x equals 6. Okay, so following on from what we were saying from the above point, if the second derivative is 0, this means that we have a point of inflection in our graph. So we have a maximum or a minimum at x equals 4, and we have 2 points of inflection, one at x equals 2 and one at x equals 6. Okay, so let's have a go at starting to sketch this function. Right, so let's draw our axes. So as I already said in the first point, point A, it tells us that f of x is 0, above 0, is positive for all values of x. So we only need to draw this half of our axes. We don't need to go down into the negative here. Okay, so let's start with point C here. So our turning point at x equals 4. So let's mark on our sketch a value of 4 for x. So as I've said, we're not told whether this is a maximum or a minimum. So what I'm going to do is I'm going to assume for now that it's a maximum and see if we can sketch a graph that fits the other points, the other statements. So I'm going to mark this here and I'm going to say that's a maximum. So we're going to have some form of turning point here. Okay. And we're also told that we have these 2 points of inflection at x equals 2 and x equals 6. So we've got some sort of symmetry going on here by the looks of things. So what do we mean by point of inflection? Well, to exaggerate that, if you think about the x cubed graph, we have that point of inflection here where the gradient changes like this. So we're going to have something similar here. So let's see if we can draw this. So we're going to have something that looks a bit like this here. So you can see we have that sort of changing gradient, this point of inflection, and we're going to have the same on this side here. It's a very rough sketch. It doesn't need to be a perfect work of art for this, as long as you're clear with the features that you're marking on. So you could even annotate this and kind of draw an arrow and say point of inflection here. If you think that your sketch wasn't the clearest. Okay, so how does this graph finish? Well, we're told that f of x is greater than 0 for all of x. So we know that it can't dip below the line. And because there's not the and equals to sign here, we know that it can't actually reach f of x equals 0 either. So we're going to have some form of asymptote that could be anywhere just above the 0 value here for f of x. So our graph is going to taper off something like that. So here is an example of a graph that fits all of these properties of this function. And if you remember, the question asked us to sketch an example of this function. So here, for this example, I assumed that the turning point at x equals 4 was a maximum. But you could have tried assuming that it was a minimum as well, and you might get a slightly different looking graph that still fits all of these properties. So if we draw our axes again, but we were to assume that the turning point, let's say it's somewhere down here, at x equals 4 was a minimum, you might have something that looks a bit like a mirror image of this graph here, like this. So we've still got our points of inflection at x equals 2 and x equals 6, but instead of tapering off to a value just above 0, we'd have it tapering off at a slightly higher value. So if you can see, it's kind of like a mirror image, just been flipped upside down. So in my mind, both of these are correct. And the question only asks for a single example, so only one is required. So I hope that was useful. I hope that made sense and has helped you answering this question. So I hope you will join us next time, where Kathryn will be taking us through question 21 from the 2012 PAT paper. So hopefully see you next time.